In this video, we're going to talk about describing location in a distribution, and specifically, we're going to talk about z-scores. What's a z-score? Also known as a standardized score, a z-score for an individual value, so that's a single data point in a distribution, it tells us how many standard deviations away from the mean that value falls, and in what direction. Is it to the left or to the right? And so there is an equation, of course, it's mathematics, to find your standardized score or your z-score. So we would say z is equal to the value, so that data point, that individual value in a distribution, minus the mean divided by the standard deviation. So z-scores that are larger than this value, the mean, have positive z-scores, and values that are smaller than the mean, again, that value, have negative z-scores. So it would make sense that something to the left is negative and something to the right of the mean is positive. If you think back to the example of 25 stats test scores all out of 50 points, where we found the percentile, that was last video, we could find this score of 43, so that was Emily's score of 43 right here. And what we would do to find that particular z-score, so its place and how many standard deviations it is away from the mean. First of all, the mean is about 35.44 out of 50. So we take that value, which is 43, subtract that mean, 35.44, divide by the standard deviation, which is that value here, 8.77. So that is 0.86. That means that Emily's test score is less than 1, but almost 1, 0.86 standard deviations away from the mean score of the class. So in particular, the relationship between the mean and the median, so our mean is right here and our median is right here. They're about 2.5 points off. It tells you about what you'd expect in this left skewed, right, because the tail's over here, the left skewed distribution. Let's continue with this example. Same data set about the stats test. Let's do two things. Let's find and interpret the z-score for Jacob, who earned an 18, and Tamika had a standardized score of 0.292, so that's a z-score. Their z-score was 0.292. Let's find Tamika's test score. So let's do Jacob's first. First things first, Jacob's score is 18. That's that score right here. There's only one score less than it. Good for Jacob. So let's find the z-score right here. Let's take the value, the mean, and the standard deviation and figure out what that is equal to. So we take Jacob's score of 18, we subtract the mean, which is right here, our x bar, and we divide by the standard deviation, this s sub x, which is 8.77. We subtract, divide, we get negative 0.199. So that means that Jacob's test score is almost 2 standard deviations to the left or smaller than the mean test score, which is 35.44 out of 50. So now let's take a look at the information that we have and work backwards to find the value. So Tamika, z-score is 0.292, so that value is going to be 0.292. That we're going to be solving for. We can find the mean and the standard deviation, so let's do a little bit of algebra to find the value. So here's our starting equation. We've got our z-score, we've got our value or our test score for Tamika that we're looking for, subtracting the mean divided by the standard deviation. First thing that I like to do here is that if I have a fraction, especially if I have a variable within that fraction, whether it's in the top or the bottom, I'm going to put this over 1, or if this was a fraction, then great. I like to cross multiply, so I get everything out of a fraction. Here we go. So 0.292 times 8.77, and then we just keep that on the right-hand side. Going to multiply these two values, going to add that value over, and find x, or Tamika's score. Adding those two things together, I get roughly 38. So that means that Tamika earned roughly a 38 out of 50 points on the stats test. Now, if we take a look at the original z-score, that 0.292, let's call it 0.3, that should make sense. Tamika's score should make sense. So the mean is about 35.44, and Tamika's score is about a third to the right number of standard deviations. So not even a full standard deviation, a third of a standard deviation. A third of about 8.77 to the right or greater than the mean. So that's how z-scores can help us identify where an individual data point lies in a certain distribution. Fun fact, you can manipulate a data set by I don't know, adding or subtracting a constant to your data values. Let's take a look at an example here. So our lovely example of our test scores, those 25 scores on a stats test out of 50 total points. We have this data here. We've been working with that data. Now let's say that that teacher added 5 points to every test score. What on earth would that do to our data? What we have here is the original dot plot. It's the same thing as that, just a little bit wider. And then if we added 5 points to every single raw score out of 50, here we go. Obviously it's out of 55 now. And here is the information that is here, but now we have the original and the adjusted. So that is +5 to everything. What changes, what doesn't? Our measures of center, so that's our mean and our median, they both go up by 5. And location, that is our minimum, Q1, Q3, and maximum. They also all go up by 5. Next, I look at the shape of the distribution. The shape hasn't changed. Every point shifted to the right 5, but that doesn't mean that the actual shape of the distribution changes. So shape doesn't change, as well as the variability doesn't change at all. So that's our standard deviation, our interquartile range, and our range. They don't change. So what can we deduce from that information in list form this time? The effect of adding or subtracting a constant means that if you add or subtract, so it either goes up an A value or down an A value, that's going to change your measure of center and location. So your mean, your 5-number summary, and your percentiles, those are all either going to add or subtract that value. What doesn't change is the shape of the distribution and measures variability. So your range, your IQR, and your standard deviation. So now that we understand what happens with adding and subtracting a constant, what would happen if we multiplied or divide by a constant to a data set? So let's take that last slide's example a little bit further and say that those adjusted test scores, the ones that were bumped up by 5 points, let's say the teacher wants to adjust them, multiply them by 2, so now they'd be out of 100 points to turn them into a percentage. So really what we're doing here is we're taking that data and we're multiplying by 2. So here are the adjusted scores, so what we did by adding 5 points to every score, and then what happens when we double them. So what do you notice about the adjusted scores versus the doubled scores? In all of our categories, I notice that mean doubles, standard deviation doubles, minimum doubles, Q1 doubles, median, Q3, max, IQR, and range, they all double. Obviously, N, the number of scores, didn't change, so that didn't go anywhere, but every other measure, center, variability, distribution, all that good stuff, doubled. But look at the shape. The shape still goes up and then comes down a little bit. Still goes up and comes down a little bit. It's a little stretched out in terms of this one, but the shape actually doesn't change. The shape's the same, but everything else doubles. And now in a color-coded list form, what can we say about multiplying or dividing by a constant to a data set? Well, we know that everything except for the shape of the distribution is either going to multiply or divide by that value. So if you multiply by 2, every single thing except for the shape is going to double. If you divide by 2, everything's going to half. So that's everything: center, location, and variability. But again, shape doesn't change. And a note to this, because multiplying and dividing is a little bit different than addition and subtraction, it's really not common to multiply or divide by a negative value. Doing so would multiply or divide the measures of variability, so that's our range, IQR, and standard deviation, by the absolute value of B. So we can't have a negative amount of variability. Think about range or even standard deviation. That is distance, right? Distance from smallest to largest, and distance from the mean. We can't really have a negative distance, even in statistics, so that's why it would be really the absolute value B. But again, it's really not common. So beware of that. So let's take all those ideas and put them into an example. So this one's called Too Cool at the Cabin. So moving away from the test scores from a stats teacher's class, but we cannot escape the stats teacher. He apparently has a Colorado cabin in the winter that can stay well below freezing. So what does his wife do? She sets the thermostat at 50 degrees Fahrenheit to prevent the pipes from freezing. She also buys a digital thermometer that records the indoor temperature each night at midnight. Unfortunately, alas, the thermometer is programmed to measure the temperature in degrees Celsius. Oh no, first world problems. Following are a dot plot and numerical summaries for the midnight temperature readings for that 30-day period, again in Celsius. So here's our dot plot. Looks like it sinks down to about 3 degrees Celsius and up to 14. A lot of 7 degrees Celsius nights there, and some at 9 and 10. Anyway, I digress. Here's our calculations. And let's do two things. Let's find the mean temperature in degrees Fahrenheit, and does that thermostat setting seem accurate? And then let's calculate the standard deviation in Fahrenheit and interpret this value. The first part to our problem is to take our mean temperature, which is right here, our X bar, and turn it into degrees Fahrenheit. Luckily for us, and I'm sure you've seen this before, there's an equation to turn Fahrenheit into Celsius and vice versa. So what we're going to do is we're going to plug that mean value in here for degrees C and multiply it by 9 over 5 and add 32 and find the Fahrenheit temperature, and then we can answer that question. So plugging in 8.43, multiplying it by 9.5 and adding 32, we get roughly 47 degrees Fahrenheit. So does that seem accurate? Now, you might think, 3 degrees, who cares? That's not a big deal. But the thermostat doesn't seem to be very accurate. 3 degrees is a lot. It's set to 50 degrees Fahrenheit, but the mean temperature, the average temperature at night, is 47 degrees Fahrenheit. So something's amiss. So now let's do the same thing. We're going to convert the standard deviation this time instead to Fahrenheit and interpret that value. So what ends up happening here is we have 9/5 times 2.27, which is our standard deviation, add 32. We get about 4 degrees Fahrenheit. So what does that mean in terms of this context? I would say that temperature readings typically vary by 4 degrees Fahrenheit. That's a lot. That's not an accurate thermometer. Get a new one. Last thing we're going to talk about in the video today is connecting transformations, so those addition, subtraction, multiplication, divisions that you can do to a data set, and z-scores. So how many standard deviations a particular data point falls from the mean. So we're unfortunately coming back to that same data set of 25 stats test scores out of 50 points. Now, what if we standardized all the values in that distribution and we found the z-scores and we plotted the z-scores of each of these individual data points? So doing that, finding the z-score, plotting the z-score in a dot plot, is what we end up with down here, a dot plot of the class's z-scores. So what this is really saying is that each of these dots is however far away, standard deviation-wise, that score is away from the mean of the distribution. So let's take a look at some identifying characteristics about this new data set. Let's talk about the shape, center, and variability of the class's z-scores. So if you remember the rules, shape stays the same. So this is the original distribution by test score, and if you notice, it's still skewed to the left. So same amount of dots, same shape, same kind of spread. Gotta love it. Shape stays the same. And next, for the measure of center, let's talk about the mean, which is a critical measure of center. So the mean for the original is about 35, but our new mean for our z-scores is at 0. So if we were to take the original mean, about 35, and we subtracted it from each of these scores, we would reduce the mean from 35.44 to 0. Dividing each of those new data values by 8.77 would divide the new mean of 0 by 8.77, which still yields a mean of 0. So the center, I would say, is at 0 here instead of 35. Lastly, the measure of variability that I think is most important here is standard deviation. So the standard deviation of all of these z-scores is going to be 1. So remember how we got all those z-scores is we took all of these individual values, we subtracted the mean which is about 35, and we divided it by the standard deviation, which was almost 9. It was about 8.77. So when you do that, subtracting 35 from each test scores, it doesn't affect the standard deviation. We're just subtracting, remember? It doesn't affect standard deviation. However, dividing all of those resulting values by the standard deviation, this last bit here, would divide the original standard deviation of 8.77 by itself, resulting in 1. So that's what happens with that variability and all the z-scores of every original score. Whew, what a time. How you feeling about this one? Did you roll a maybe? I don't know. Okay, it's time for me to sign off. Thanks for watching.